Welcome to the Crazy Hat Chemist. So another video here on Kinetics. So let's get moving because we got a fast rate law going. Bam! So here is an application of the integrated first order rate law. Okay? Table sugar, otherwise known as sucrose, which is a disaccharide, decomposes to simpler sugars. Those two simple sugars would be glucose and fructose. It uses a first order rate process. If the original concentration of sucrose is 0.010 molar, A, how long will it take to drop the sucrose concentration to 90% of the original, and B, what is the concentration after 300 minutes? Okay, so we got to use the integrated first order rate law. So first we need to write that down. Okay, and we also need to know what the rate constant is. This would be given. So at 25 degrees Celsius, the rate constant for this decomposition reaction is 0.21 per hour. Okay, and here is the integrated first order rate law. So hopefully you review the previous lecture that I gave on the integrated first order rate law. All right, so we're going to solve part A first and then part B. So let's get moving with part A. Here we go. So we have 90% of the original. So we're going to take that original amount that we have, and that's 0.010 molar. That's our concentration. We're going to multiply that by 90%. So that's 90 divided by 100. And when I do that, I get 0.0090. Okay, now I have originally 0.010 concentration, but I'm going to move and it is going to decrease by 90%. So I have the original amount minus the amount that it decreases at 90%, and this is the amount that remains, which is 0.0010 molar. So that's my amount that remains afterwards. Okay? All right, so now what we're going to do is plug this into the integrated first order rate law. Okay, so my top part, which is x sub t, is the amount that I have, okay, at time t, which is the amount that is at 90%, right? After 90% is gone. And then in the denominator, I have the x sub naught, or the x sub 0, and that is the amount of concentration of original amount. Okay, and that's why that's 0.010 molar. Okay, I've also plugged into this equation here the rate constant, which is 0.21 per hour. Now I'm going to solve for the time. So slowly solving this here for what you want. So what I've done is I've done the little division there, the 0.001 divided by 0.010, and I get 0.1. Okay, that's that first step. Now I'm going to take the natural log of 0.1, and I get negative 2.30. That's going to be equal to negative 0.21 times t. And I'm going to solve for t, so I'm going to divide both sides by negative 0.21. And then I'm going to get this number, t is equal to 10.95. I'm going to have only two significant figures on this problem, so I need to round this, and I need to put the correct units here. Notice that the rate constant was per hour, so when I solve for time of t, that would be hours. And so I have 11 hours is how long it will take for that sucrose concentration to drop to 90% of its original value. All right, so that was part A. Let's see if we can do part B here. Okay, here is part B. I got 300 minutes. Now, this is something that I referenced in when I introduced the integrated first order rate law. And I said that the time and the rate constant need to be in the same set of units for time. That is, t for time needs to be in whatever units, like seconds, and then the rate constant is per second. Okay, now this problem has the rate constant in per hour. So what I've done is I've changed my time of 300 minutes and I've converted it into hours, and that would be 5 hours. So hopefully you can see that simple calculation right there. Okay, now I plugged into the integrated first order rate law. So I am solving for the concentration at 300 minutes. So that is x sub t. So I know the original amount, that's x sub naught, or x sub 0, which is 0.010. Okay, I have the rate constant, that's 0.21 per hour, and I have the time at 5 hours. Again, you need to make sure that your rate constant and your time are in the same set of units so that you can cancel them out. That's one of the biggest mistakes that students make. Okay, now, and this is another thing that I brought up when I brought up the integrated first order rate law in the previous lecture. And that is, you need to know, the way back from Algebra 2, or maybe it's even pre-calculus, how to deal with the natural logarithm. Okay, so natural logarithm of x of t divided by 0.010. So that's actually a subtraction problem. That division problem becomes a subtraction problem, and that's what we're going to do right here. I've also cleaned up the right-hand side of the equation. I've got rid of the time of hours. Those have canceled out, and I've done the multiplication of 5 times the 0.21. Okay, so I've got on the left-hand side natural log of x sub t minus natural log of the initial original concentration of 0.010 equals to that product of the constant and the time. Okay, now I need to get the natural log of 0.01 and plug that in, and there's that value. Now I need to be very careful here and take heed of your subtraction and minus signs here. Okay, so it was a negative in front of the natural log, but the natural log of 0.01 is actually a negative value. So those two values right there, I got a negative times a negative, that's a positive. Okay, really simple, easy math, but yet a simple time to make a silly mistake. Okay, now I've moved that number, the 4.6052, over to the right-hand side. I got natural log of x of t is equal to negative 5.6552. Now, how do you get rid of the natural log? There's another button on your calculator that's a small little tiny e. Okay, and it's a lowercase scripted e, and that's the opposite function, just like addition and subtraction, multiplication and division. Okay, and that's what we're going to do here. We're going to use that button. That will get rid of the natural log, and then I got x is equal to this value after I plug it into my calculator, and that will be 3.5 times 10 to the negative 3 moles per liter, otherwise known as molarity. Okay, that's two problems right there within one of an application of the integrated first order rate law, first order rate kinetics. Fantastic example. Okay, I am the crazy hat chemist, and I got a crazy hat. This is a pizza hat. Hopefully you can see that. Combination pizza or pepperoni. I'm not. Oh, yep. I think it's a pepperoni combination pizza. Okay, give me a thumbs up if you like that video. Give me a thumbs up if you like pizza. And subscribe to my YouTube channel, and I'm going to see you next time. Bye for now.